Well, God, I hope you took a break after that last video. Ugh, really dismissed. Go away. Okay. That the last one is definitely a tough one. Trying to learn how to do those empirical formulas via combustion problems is one of the more challenging problem types that we do. So hopefully, breathe. This one will be quite a bit easier. Trust me. This one is not as bad as that one is by far. So this little video here, we're going to take a look at the quick distinction. Again, we're going to revisit the difference between an empirical and a molecular formula, and then how to use that concept of molecular formulas to go that kind of that next step with empirical formula problems. Again, this one should be quite a bit shorter. So sorry about that last one. I knew that one was going to be had. I didn't want to scare you off in the front in the beginning. So empirical formulas. Again, remember what an empirical formula is. Empirical formula is the simplest ratio. Simplest ratio. It's going to be simple whole numbers. It's something just a real basic concept of what that ratio of elements is present inside a compound. The molecular formula is more an example of what it really exists like. How does that particular compound truly exist within a cell or a system or whatever you want to call, whatever you want to talk about? So let me give you an example before I do these sugar ones that's on here. So for example, if we are talking about the concept of water, H2O, simple one, right? I can't reduce this down any further. Its empirical formula, its molecular formula is H2O. That's how it exists. But its empirical formula is also H2O. There's no different, MF and EF. Those are exactly the same kind of thing. You can't reduce a 1 to or a 2 to 1 ratio any further. But there's another compound out there, which is hydrogen peroxide. And a lot of students ask me about this, like, well, why don't we reduce that down? And I've mentioned this before, that peroxide, that ion is a twin ion, where those two always have to be together like that. However, its empirical formula is not H2O2. We can simplify this thing down, and the empirical formula of hydrogen peroxide is 1 to 1. It's HO, stand of time, right? Ho ho. But its empirical formula is a reduced version of its molecular formula. If I wanted to talk about hydroxide, they're the same, right? Hydroxide and the empirical formula, molecular formula, are the same. But for H2O2, they are different in terms of what they look like. That simplest formula versus how it actually exists in the molecule. This is really important, especially in organic chemistry, where we tend to see that living cells really like to make compounds that are sort of repeated units, kind of all glued together. And the sugars is a really good example of them, of this sort of empirical formula, molecular formula kind of thing. So if you take a look at sucrose, if we limit this down, if we reduce it all the way to the simplest formula, we get a simple formula, divide each of these by 11, right? CH2O. That's as simple as it gets. Glucose is also CH2O. Again, all I'm doing is looking for that simplest ratio, divide each thing by the smallest number. It gives us that simplest formula. Fructose, CH2O. In fact, all sugars have the exact same empirical formula. That's why sugars is sort of a category of chemicals, right? They have the same empirical formula, but some of them are built up as multiple versions of it. So like sucrose is the empirical formula times 11. Glucose is the empirical formula times 6, and fructose is the empirical formula times 5, right? And there's bigger ones and smaller ones that could go even larger than that if we want to. So again, an empirical formula and a molecular formula are related because you can either think about it as reducing down, you reduce the molecular formula down to find the empirical formula, or go the other direction, you multiply up, right? The empirical formula is the simplest ratio. Some multiple of that empirical formula will be the molecular formula. It's always a multiple of it. So 5 times this would give you fructose, 6 times would give you that one. So again, empirical versus molecular formulas, they always have that same basic ratio. They always have the same percent composition because they always have the same basic ratio. But the empirical formula is much smaller, and its molar mass of the empirical formula would be much lighter. So think about the empirical formula, the mass of this thing, right? It's just 1 carbon, 2 hydrogens, and 1 oxygen. That's not a lot of mass. The molecular mass of sucrose compared to the empirical mass, this is 11 times heavier. So if I know the mass of this, and I know the mass of that, you can figure out the multiple relationship between the two. So that's the big idea, is that empirical formulas are the simplest one. Molecular formulas are some multiple up. By the way, there are certain formulas that look like they should be reduced down, but you can't. This is an empirical formula and a molecular formula. You cannot reduce this down any further because there's only one sulfur down there. You couldn't say it's like H, S a half, O2. You don't reduce down to where you've got fractions on there. So there may be some things that can have some coefficients in there, look like they should be reducible, but they're not. Make sure you can take everything down, divide each thing by the same value to get it to reduce. So here's an example of how we're going to apply molecular formula and empirical formula to a compound. So whenever you have a problem that's asking you for what's the molecular formula of the compound, always start by determining the empirical formula. This is important. These are two-step problems. They're kind of multiple step. This part right here is later. So kind of pretend like this doesn't exist. Pretend like that part isn't there for right now. You've got to be able to do the empirical formula first. So this one should be pretty straightforward. 26.7 grams of phosphorus. Again, when we have percent, we can deal with them as grams. 12.1 grams of nitrogen and 61.2 grams of carbon. So those are our three elements. Let's figure out what our empirical formula is. And once we know what our empirical formula is, then we can use this molecular mass to figure out what its molecular formula is. So when I'm doing my conversions, again, when I'm doing these empirical formulas, always convert grams to moles first. Phosphorus is molar mass, 30.97 grams equals 1 mole. Again, this is for phosphorus. Nitrogen, 14.01 grams equals 1 mole of nitrogen. I don't know why I'm looking because I know these all. So hold on. Sorry, things keep popping up from a different group that I'm working with. Grams of carbon versus 1 mole of carbon. There we go. And now we just do all of our little divisions on there to make those things happy. So 26.7 divided by 30.97 gives us 0.86, I don't know, 2, something like that. 12.1 divided by 14.01 equals 0.863, and 61.2 divided by 12.01 is really 5.09. So 5.0, well, almost 5.10, 5.096, something like that. So again, students sometimes will ask me like, hey, Miss B, why aren't you like rounding these to sig figs? These are sort of like in progress numbers. Remember, we don't round to sig figs until the end. So as long as I'm keeping like an extra couple of digits in here, I'm actually pretty good. So I want to keep it to at least my 2 decimal places. I'm trying to keep 3 sig figs. So I'm trying to keep center 3 sig figs as I'm doing these. And they tend to end up working themselves out. Because again, these are not final answers. So I don't quite have to worry about it the same way as if I'm rounding a final product. So I'm doing my step where I'm dividing it by the smallest number to see if I can figure out what that ratio is. So 5.10 divided by 0.862 gives me a value of 5.92, something along those lines, which is pretty much, I would say that's closest to 6. That's the closest enough one to make sure that one's ready to go. So I'm going to call this 6 because that 5.92, that's not a fractional. If you're at that 0.9 point, that's basically close enough to a whole number. So this is where I can kind of fake it and round it. So here is my formula, PNC6, some random weird thing. So now this is my empirical formula. It's PNC6, right? P, N, and then C6. So what I need to do now is figure out what the relationship is with its molecular formula. Okay, well, I know the molecular formula is heavy. It's 580 grams, approximately, okay? And I know that this has to be some multiple, this will multiply up to be the molecular formula. The molecular formula is a multiple of this. Maybe it's times 2, maybe it's times 3, maybe it's times 5. I don't know what it is. That's what I'm trying to figure out what that would be, but it's got to be some multiple of that. So let's figure out how much this thing weighs. Figure out your empirical mass. So my empirical mass is phosphorus, 30.97 plus nitrogen, 14.01 plus carbon times 6. So 30.97 plus 14.01 plus 12.01. And I get a mass here. That can't be right. 30.97 plus 14.01 plus 12.01. Let's try this times 6. There we go. I knew that was right. 117. 117 point something 04. But it's basically 117. So now I know that some multiple of this mass is going to equal this 580. So what I want to do is, rather than try to multiply up and guess and test, just divide, go the other direction. 580 divided by 117. And I get a value of, 4.957, basically 5. That means that it's this multiple. If I take 117 times 5, I get this 580, which means that my molecular formula is 5 times my empirical formula. So I'm going to take my empirical formula and I'm going to multiply it by 5 to get my molecular formula. Again, why did I do this? I took my empirical mass, figured out what that was. So the lowest possible ratio, 117. I knew what the molecular mass was because that was given to me. I divided these two to figure out what the multiple is. Is it 2 times, 3 times? Turns out it's 5 times. So now I know that my formula, my molecular real world formula, is 5 times my empirical formula, also known as P5, N5, C, 30. That's big. Yep, and that should work itself out. So that's how you deal with the difference between molecular formulas and empirical formulas. So when you have a problem that's asking you about that molecular mass or that molecular formula, and it gives you a molecular mass, don't use that right away. Use that at the end. It's a second kind of component of it to figure out what your multiple is. Because remember, that every one of these would be a multiple of its big brother, right? These are like the little ones. I know that if I know this mass, 11 times that mass will give me this mass. So that's a relationship between empirical formulas and molecular formulas, or empirical masses and molecular masses. So there you go. Hope that made some sense. We'll practice some more in class. See you guys later.